everyone, it's Raph here with the second instalment of my lecture series on stats and how to think about them in the context of papers. And today we're going to be talking about p-values, which is I think a bit of a tricky concept for us to get our heads around, and then also a bit about power and confidence intervals and how these relate to how often our results might be wrong. So hopefully by the end of this lecture we'll have a bit of a better understanding about what a p-value is. We'll be able to relate this to understanding why multiple testing is such an issue, and we're also going to be able to understand some maybe more complex ways of presenting probabilities like confidence intervals and how to interpret them with regards to clinical decisions. So before we dive into talking about p-values and confidence intervals, just a quick note on the null hypothesis, which is something that you'll hear a lot when talking about research. Null as a word means to have no value, and essentially what this null hypothesis is this acceptance that we have no knowledge at the beginning of a trial, and that's the thing that we have to disprove. So in a randomly controlled trial, we've got no knowledge about there being any difference between A and B. In an observational study that we have no knowledge about a link between cancer and smoking. And so our null hypothesis is always that there is no link between these things, and that is the hypothesis that we have to disprove using our p-value to show that we actually think there is a difference. So all of the time I talk about disproving the hypothesis, that's disproving this idea that there is no difference between these two things. So what is a p-value? Try just out loud, frame how would you answer this question, and have like 10 seconds to do that. So I think a common way we interpret p-values is sometimes the chance of the result being wrong, or we think of it in paper terms of how big or important the effect is, and say it's statistically significant, and that means it's an important effect. But actually a p-value is based in this idea of a null hypothesis, and the null hypothesis for any experiment is essentially that the two things you're comparing are the same. There's no difference between them. And it accepts this and it says, okay, if that was true, how often would we get this result just by random chance? So what a p-value is saying, if it's 0.05, is that if you compared anything, the numbers drawn from two packs of cards that are identical, anything like that, how often would you find a difference that is this big 5% of the time? And this is a value that we use kind of arbitrarily, because we've decided 5% seems like a reasonable amount of the time to be wrong and say there is a difference when there in fact is not. But the problem with this is in the way we set up and design studies, we can sometimes manipulate this. So although there's a 5% chance of this happening, even if there was no difference between these two groups, that's only true if we're designing our studies in certain ways. And that doesn't mean that there's a 5% chance of a result being wrong. And we'll talk a little bit about why that is the case. And this is just reinforcing that point that assuming a normal distribution, that the line seen here is roughly what we mean when we say the p is 0.05. So it's on such an extreme amount away from the middle of where we would expect if there was no difference, that it would only happen about 5% of the time. And that's roughly 2 standard deviations away from the mean, 1.96 to be precise. Okay, moving away from the p-value, which is assuming that there is no difference, power is a slightly different concept. And power is the idea of if there is a difference between these two things, that's a certain size, how often will you detect it given the way you've designed your study? And this depends on a number of factors that have gone into your study design. And that's how big you think this difference is. So it makes sense. The bigger your difference, the higher your power with a certain number of people. You need less people to find massive differences and a lot more people to find small differences. Cohen's d is a way of measuring how big a difference is that you don't need to get too involved in. how big your trial is. So as sort of previously alluded to, bigger trials are able to find smaller differences. So the more people you have, the more the higher your power will be for any given effect. The variation in the population is something we don't necessarily think about, but traits that are very variable, it's going to be harder to find differences between. So if you've got a trait like height that is quite different between two groups, let's say men and women, and isn't that variable, you might be able to find a difference very easily. Whereas if you've got a trait like mood that might subtly differ, for example, let's assume that it does between sexes, then, and there's a lot of variation in the population, a lot of people who are completely fine, and then some people who are like really depressed, then it might be a lot harder to bring out those differences because there's just a lot more noise in the population. And the final thing that changes power is your significance level, or alpha, and the one that we normally use is the 0.05. And essentially, the lower your significance level, the lower your power. So the more that we try avoid getting it wrong and saying there is a difference when there isn't, the worse we are at being able to determine that there is a difference when it actually exists. And this is the balance that exists between power and p-values. We can think of this as a comparison to sensitivity and specificity, which I talked about a little bit in my test lecture. If we're thinking of our trial as a medical test, the significance level we pick is specificity. It's if there is no difference between these two things, how often are we going to be wrong and say there is, even though there isn't, that false positive idea. Whereas the power of our trial is our sensitivity. So if there is a difference between these two things, how often are we going to pick it up? And these two things are always in balance. It's a balance between these two types of error, type 1 and type 2. So the more that we try avoid calling it wrong and saying there is a difference when there isn't, the worse we're going to be at picking up those differences when they exist. So these two types of error get bandied around a lot, and it's very confusing to remember which one is which, so I thought I'd go through them briefly. So the type 1 error is that false positive error. So it's rejecting the null hypothesis there is no difference when it's true. So when we say, okay, medicine B is better than medicine A, but actually medicine A and B are pretty much identical, and that's related to the p-value or the significance level. Whereas type 2 error is the opposite, so saying we've not found any difference between these two medicines, when in fact, in reality, medicine B is better than medicine A, so a false negative finding. And that is related to power that we talked about. And yeah, just going again, comparing to sensitivity and specificity, type 1 error is a false positive and type 2 error is a false negative. And I find this quite hard to remember. I find it hard to keep in my head what's type 1, what's type 2. So there's a couple of mnemonics I found on the internet to help remember. And the second one of which is type 1 is 1 false, so it's a false true, false positive. Whereas type 2 is a false negative, so it's like a false false. So there's 2 falses in type 2 and 1 false in type 1, and that's a way to remember it. Or the other one is when a boy cried wolf, the village committed type 1 and type 2 errors in that order. So when he cried wolf initially, he said there was a wolf even when there wasn't. That's a type 1 error. And then obviously when he gets eaten, they don't come when they should have, and that's a type 2 error, a false negative. So these are sort of handy ways of trying to keep it clear in your mind which is which. So what's the takeaways from this? I guess the message I'm trying to get out is that research is a balance of which p-values drive the specificity, how good we are at not saying there is a difference when there isn't one, and power drives that sensitivity, so how good we are at finding those differences. So what does this mean? Well, it means that if we think that we're deciding that 0.05 is going to be our cutoff for saying, well, there probably is a difference, this means that every time we do a piece of research, when there is no difference, we're rolling a dice. And if it comes up 1 in 20 times, we're going to think there's a difference, even when there isn't. And this is important in specific situations. It's important when we're doing lots of tests. And that's because the more tests we do, the more dice we roll, the more times we'll find that 1 in 20 chance. If we roll 1 dice, yes, there's a 5% chance of it coming up. But if in each study we're rolling 20 dice, then we're probably going to find one that's significant even if actually in reality there's no difference between these two populations that we're looking at. And this is the whole concept of multiple testing and why it's quite dangerous and something that we should be very aware of when looking at studies and when designing studies. So to get this idea a bit clearer, I've tried to go through an example, and I've taken psychics, so apologies if anyone is an ardent believer in psychics, but I'm going to assume that we're trying to test whether psychics can predict the future. And we think only some people have this ability, not everyone's a psychic, and we're going to gather 20 people to predict the outcomes of coin tosses using their powers. The person will toss a coin, look at it, and they'll try read their mind and see what they've come up with to see whether they're going to be able to predict it. And then we're going to assess all these 20 people who claim to be psychic, and we're going to assess whether they're better than chance. And if they are better than chance, we're going to say, well, there seems to be some evidence that they're able to sort of read this person's mind and be able to tell what they've flipped their coin to be. So if we set up our experiment like this and we assess each person individually, what are the chances of us finding someone who we find statistically significantly to be psychic? I'll give you 10 seconds just to come up with a guess. Well, let's assume that psychic powers don't exist and that none of these individuals have psychic power. So essentially, power doesn't matter, it's all about the significance value. And remember, our significance value, we're going to accept 5% because that is a reasonable one, that's what's scientifically accepted. So if every single person has a 5% chance of us just by finding that they're too different from the mean to explain by the null hypothesis. So yeah, oh, this result would only have come up about 5% of the time if there was no difference. But of course, we're not doing that test once, we're doing it 20 times. And actually, if you do the maths, the chance of you finding that at least one of these people is significantly different and therefore potentially ending up declaring, oh, this one is psychic, the rest aren't, but this one is, we found statistical significance for them, is 65%. So you end up doing 95% to the power of 20, because basically there's a 95% chance for each person that they won't find this difference, and you do that to the power of 20 to find the true probability. But over half the time you will find someone in this population who is statistically significantly better than chance. And that's a problem, I guess, because if you're not transparent or not aware of this, you'll go away from that thinking, well, I proved that psychics are a real thing, that they exist, that I've got statistical significance for this person, and therefore they are psychic. And this happens in research in several ways. Because obviously this is a bit of a spurious example, this isn't something that people are going to do. But in actual research, we've got unplanned subgroup analyses, which often bring these up. So your main analysis on your main group doesn't work, you say, okay, well maybe it works in men, oh maybe it only works in women, or maybe it only works in people over 65, maybe it only works in young people, maybe it only works in people who are black, maybe it only works in people who are Caucasian. And you keep running these subgroup analyses, and each time you run one of these, that's a new population, and that's a new chance to have that 5% to come up and be wrong. And so we've got to be really cautious about those, because there's a good chance that they're going to find spurious results. The other way is measuring excessive number of outcomes. So you don't measure one way of does their blood pressure improve. You measure 17, 3 of which are questionnaires, 5 of which are objective measurements using different machines. And again, that's just ticking up the number of chances you have for that 5% to come up and you to get a spurious result. And finally, there's a whole idea also of publication bias. So, you know, maybe instead of you measuring 20 people here, there's 20 studies going on about psychics. And the 19 studies that don't find anything, they don't report it, because who's going to publish studies saying psychics aren't psychics? That's a bit boring. But the one study that does, that's an amazing finding. That's definitely going to get published. And so you end up being biased towards publishing only the studies that have positive results. And so actually the amount of these spurious findings that we see are enriched. And that's a big problem in things like psychology. This is XKCD cartoon to sort of illustrate this idea and why it's a problem in often epidemiological and dietary studies. So, you know, someone has an idea, maybe jelly beans cause acne, and they don't find any link, but well, maybe it's just a certain colour. So they're doing these subgroup analyses, and so they run it on every single colour, and you know, there's lots of colours of jelly beans, and most of these don't turn anything up, but one does, green does. And when they report that result, they don't go, we looked at all the different colours and only one came up and this means it's probably chance. No, that's not an exciting headline. The headline is green jelly beans cause acne. And this might seem absurd, but this is what we see in all these nutritional studies when one substance gets linked to cancer and then the next week it gets linked to protection from cancer. And it's because a lot of these will have food diaries with 100 different types of food, and then they're just linking them, seeing is there any correlation with cancer. And by chance, a few of these will come up and they'll get published and then they'll get reversed in the next sample because there isn't a true link. And of course, sometimes there is, but we have to be careful to avoid doing this to undermine faith in science. So I sort of talked a lot about the problems and how this is an issue, but how do we solve this? And well, one way is to say what we're going to do before we start our trial. So most trials need to have a primary outcome, which is one, maximum two things. As you say, these are my primary outcomes. And then instantly, and you have to keep them, and instantly if you don't find significance in your primary outcomes, people are a lot more suspicious. They're like, well, they got a secondary outcome, but their primary outcome wasn't there. And so the result becomes a bit less trustworthy. You can correct your p-value for multiple tests. There's various different ways of doing this that I won't go into too much detail, but the simplest one is to divide 0.05 by the number of tests you're doing. That's not the best way to do it. It's called the Bonferroni correction. And there's other better ways of doing it. The third way is to just, as a reader, be suspicious of subgroup analyses. So if someone hasn't found an effect and then has, when they've split their population into two different groups, it might be there, but be suspicious of it and look for maybe lower p-values than you would normally. So, you know, if they do a subgroup analysis and their p-value is 0.0001, then actually that's relatively convincing. That's quite a low chance of coming up if there is truly no difference. I mean, you need to run a lot of subgroup analyses to find that kind of result. But if it's sort of near the 0.05 mark, that's much more likely to have come up by multiple subgroup analyses. And last is to replicate. It's a massive problem in science, sort of lack of replication, especially sciences like psychology have recently come out and sort of had to think about how to do this. And we need to replicate results. So if you find something in one of these subgroup analyses that looks interesting, go and look somewhere else for it and see if you can get that result again, because if you can, it's much more likely to be correct. So, focusing back to power, I'm going to work through some examples for us to think about, in the grander scheme of things, how does our power and why is power important, and how does power affect the amount of correct results we're going to get when there's lots of scientists out there doing studies. So we talked about how power is a function of all these different things, but the one thing really that we can change is how big our trial is and our chosen significance value. But actually our chosen significance value is relatively fixed. 0.05 is just the one that people tend to adopt. So how big our trial is the main way that we influence power, and bigger trials mean better power. And just again, going back to that comparison to sensitivity and specificity, our power is going to determine those type 2 errors. So when we say there's no difference between these two drugs that we can find, but actually in reality there is a difference, so a false negative. And you might be familiar with these tables more from a sensitivity and specificity point of view, but we can think of our medical trials power and p-values as being equivalent to this if we change the table to look like this. So, you know, that actual difference row is saying there is a difference, and the chance that we're going to find a statistical significance is essentially our power, so as a proportion of the number of actual differences there are. So if 20 drugs are different and our power is 80%, we're going to find 16 drugs that are different. And statistical insignificance is the opposite, so the inverse, so the rest left over after we do the power. And vice versa, if there is no difference, so however many drugs or different things there is no difference in, we're going to find 5% of them to be significant, and the rest of them we'll find to be insignificant. And this is important because it means that on a population scale, so we're looking at all the drug results that come out as being significant and useful for patients, that it's not just power that influences how likely you are to be correct, but also the base rate, or how many of the drugs we're testing that are actually helpful. A bit like in a disease, it's not just the sensitivity and specificity of the test that affects whether a positive result means that you have it, but also how common it is. So, and we're going to sort of go through a similar example about how, like in a rare disease, trials where most of the drugs we're testing aren't working mean that our results are going to be less trustworthy. And then also there's another issue of internal quality. So, putting aside power and statistical significance for a second, if your trial is a rubbish trial where you're introducing loads of biases, it's going to be more likely to be wrong. And we'll cover how to think about assessing a paper and trials for bias a bit more in a subsequent lecture when I talk through how to read a paper and think about bias. So we're going to run through an example to think about how trustworthy scientific results that come out are. And so in this scenario, there's many scientists trialing many sets of drugs against placebo. It's a scientific world, they're all doing these trials in parallel separately. But only 20% of these drugs are actually effective, and that's our base rate. 20% of drugs out there in this trial, the hypothetical scenario, are actually effective. Also, trials are expensive, these guys are struggling with funding, so all the samples being used are too small, so the power, so that's the chance of us detecting the effect if it's there, is only 40%, so not that high. We normally aim for about 80% traditionally. So if all of these things are true, and just try guesstimate, so of 100 drugs that we test separately, all in individual trials, of the ones that we decide these drugs are beneficial for patients, how many are actually going to be beneficial? The best guess, I'll give you 15 seconds to have a think. So we'll go through this using my handy pictograms. So we've got 100 trials, 100 drugs here, all being assessed individually. 20% of them are effective, as depicted. So for the effective ones, remember, power is the main thing that's going to determine whether we find them. Our power is 40%, so 40% of the time we're going to find there's a statistical difference. So 8 of those 12 we're going to find to be effective. For all the ineffective ones, it's our p-value that's going to drive our significance. So 5% of our p-value, so 0.05. So 5% of these will find, oh, if there was no difference, there's only a 5% chance this would rock up. And if we do that, out of the 80, that's about 4 that we find to be significant, even though there's no true difference between those drugs. And what does this mean overall for when we actually on the other end see a drug that's gone through trials and been found to be effective? Well, actually, we find 12 drugs to be effective, but only 8 out of 12 are actually effective drugs. So there's only a 66% chance that a drug that goes through this process that we find to be effective is actually effective for patients. Another important thing to recognize is, just like a p-value of less than 0.05, it doesn't mean that there is actually a difference between the two things you found, and it doesn't mean that there is actually a difference with a 5% chance. Similarly, a p-value of greater than 0.05 doesn't mean there isn't a difference. We can see here, because our power is so poor, actually, in most of the drugs that are working, we're not going to find a p-value of less than 0.05. So it's important to not interpret the p-value as the chance of a result being wrong or right, the chance of a difference being present or not. Because if your power is really poor, a p-value of greater than 0.05 tells you very little, because we'd expect the vast majority of the p-values of things that are actually different to be more than 0.05. And this is the sort of diagrammatic work through of that. Feel free to pause and check this so it makes sense, but it's sort of saying the same thing, and that this sort of 66% is like equivalent to our almost like positive predictive value in tests, and the 86% to the negative predictive value, with the 40% being our sensitivity and the 95% being our specificity. So the specificity is like the reverse of the p-value. And again, just to help you make sense of this table, I've put in the numbers from this example. So here you can see we've popped in the power there, 0.4, and then 1 minus power, 0.6, and same with the p-value. And we've popped in the numbers of actual differences and no differences. And the numbers we get out are the same as just talked about. So that 8 and 4 and 12 and 76. So this is just how that example fits into this table I showed you a bit earlier. So how does this change if our experiments are better? Well, in the subsequent example, it's still an infrequent event, the drugs are still quite rare, but actually we've thought about our design a little bit, and we're going to adequately power our studies probably by using more people. So now, 80% of the time when there is an effect, we'll find one. Well, the setup's going to be much the same here, but unlike before, we're going to discover 16 of those 20 drugs truly to be effective. In contrast, for our ineffective drugs, the same. Our p-value hasn't changed, the same's going to happen. We're going to find 4 to be effective even though they're not. And this time, that means that actually 16 out of the 20 drugs are actually effective. So this time, our positive predictive value is in a way 80%. 80% of the time when we find a drug and we say this by trial, this drug was found to be effective, it was actually effective. And so you can see that increasing our power is excellent because it increases the chance of a result we find actually being right. For the final example, we're just going to keep the power the same at 80%, but this time increase the base rate, so actually 50% of the drugs looked at here are effective. And so here you can see the population is a lot more balanced. And this means if our power is 80%, actually, again, 80% of 50, which is 40, we're going to find to be effective. There's less ineffective drugs, so it's 5% of 50 this time, which is about 2.5, so I put 2 here for convenience. And this means that actually the vast majority of drugs we find to be effective are truly effective. And again, you can pause to look through this, but it's just the diagrammatic work through that. So we can sort of see here that intuitively the chance of a drug that we think actually working is related to the power, it's related to the significance level, which we haven't changed, but if we make that significance level different, it will have a complex effect on this, and also how often our event occurs. And this might seem like something we can't affect, but actually it is something we can affect, because this is why hypothesis-driven research, so actually this drug does this, and there seems to be a plausible reason for why it might be able to affect this disease, we'll probably have a higher base rate than if we just go, well, maybe these drugs work, we're going to try 100 drugs and see if they work, a so-called fishing expedition. And that's the problem with, again, lots of those nutritional epidemiological studies, because they don't necessarily have hypothesis drive behind them. And that's why we need to be a little bit more cautious interpreting those sort of studies, rather than we've got a clear reason why this drug should work, there's some evidence it works, and now we're doing the trial. Because actually a positive result from that trial is more likely to be trustworthy. So yeah, so solutions again are that hypothesis, thinking about why we're doing research. That's not to say that we can't ever do screens, we just need to be careful and design those sensibly. So in a GWAS, which is a genetic study where you basically look at all the genes in the entire genome and check whether it's related to a condition, what they do is they use very, 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 very stringent p-values. So p-values orders of magnitude smaller than 0.05 to make sure that their chance of finding a result, even if there is no difference, is very low. We should be suspicious of positive findings when the base rate is low. Actually, you'll often have noticed that there's lots of studies that come out in preclinical studies or early trials being like, oh, it looks like this drug is effective in this wonderful way. Unfortunately, a lot of those fail, and part of the reason is, we've demonstrated in animal models and those are different to human models, but part of that is that that's a lot more exploratory, there's a lot more work going on, and if it's a bit less hypothesis driven and a bit more, there's lots of different things going on and the base rate of actually true findings is likely to be low, then results that do get through are more likely to be by chance rather than because of a true effect, because of what we just went through. And finally, the last message is that trials should be designed to have good power calculations. Good power. And the reason for this is if generally we're doing trials with good power, that means that the results that do come through are more likely to be real. So on a systematic level, it's important that most trials we go through, unless there's a very good reason, are well powered. with exceptions for like pilot studies where you're just trying to see, does the trial setup work? And if you're trying to make a judgment about whether a drug works, your trial should be adequately powered. So what are our takeaways overall from this section of the lecture? Well, hopefully you understand problems with and examples of multiple testing and why that can change our interpretations of a test and mean that results we get aren't valid. Hopefully you understand a bit that power, p-values, and base rate can actually affect the chance of a result being wrong, which is that's not what the p-value represents, but the p-value affects the end. You see that result, is it right or wrong? And hopefully you understand some research-based solutions and how to implement them in order to stop these problems. In the next section of the lecture, we're going to talk about moving away from p-values. So there's been a bit of a trend in research to move away from this binary interpretation to a bit more of a subtle, complex interpretation. And this often involves confidence intervals and also thinking about clinical significance. So why move away from 0.05? Well, as discussed, it's an arbitrary figure. It's designed that overall 5% of results will get wrong. And it sometimes results in these, obviously a little bit silly distinctions where 0.049 gets lauded as a significant finding that you can go and move forward with, whereas 0.051 doesn't reach significance, or trend is often used when you're trying to sort of almost say it's sort of almost significant. And that means that you have these differences that don't really exist, and I think there's a growing acknowledgement of that, and that actually we need to see the p-value more as how often would this have occurred by chance, and what does that mean about how we interpret it or use this finding. So this more realistic gradient of a p-value, where the closer we get to 0, the much more likely it is to be trustworthy. Because similarly, if a result of clinical trial is 0.05, a randomized trial, there's a 5% chance that's happened randomly if there's no difference. If the p-value is 0.0001, we can be, if that trial was well run, we can be as certain as we're going to be that there is a true difference that one drug is better than the other. So even within significance, there's a gradation, and vice versa. As things cross that 0.05 boundary, there's still some evidence there's difference there. That result would only have happened 7-8% chance if there was no difference. Yes, that's probably a bit too weak to then move forward as a clinical treatment, but that's not too weak to think about we need more trials to look into this. So it's changed from this binary there is or isn't significance to what is the degree of evidence that there is a difference between these two things, which is a more realistic view. The second thing is this idea about clinical significance. So all of these values, the p-values, everything else, is statistical significance. It's thinking about the null hypothesis, there's no difference, what's the evidence there's any difference at all. But we're not just interested in, is there any evidence these two are different at all? We want to know if that difference is meaningful to us as clinicians and to the patients. So, if medication makes you feel better by 1 out of 1,000 on a depression scale, or reduces blood pressure by 1 millimeter mercury, we don't really care. We can be almost 100% sure that there's definitely a difference between these two drugs. But if that difference is tiny, do we care about that difference? Probably not. So there's starting to develop an ideas of evaluating drugs not around are they or aren't they different, but is there a clinically meaningful difference? And that's quite a complex idea. And something that, there's a lot of debate about how exactly do you define clinical significance, and that's something that requires, discussing with patients and saying what do they care about a change in their depression scales, or looking at epidemiological studies and how much of a change on blood pressure makes a difference to a person. So we're not going to get into that too much there. The last segment is confidence intervals. So looking at a confidence interval rather than a p-value. And I thought we'd try again, just how would you define a confidence interval, and give you 10 seconds to come up with your definition. So confidence intervals are something that there's a lot of debate about exactly how you should define them, depending on your sort of philosophical approach to statistics, which I won't go into too much because I'm sure that people generally aren't too interested in that. But I guess our instincts are to interpret it in a more Bayesian way, so that there's a 95% chance that the true value lies between these confidence intervals. But to be honest, most of medical statistics is done in a more frequentist manner, and that's sort of a bit less intuitive and involves saying that 95% of the time, if you ran the experiment that you did, you would have the value would lie between the two ends of the result that you got, which is a bit more complex and requires thinking about an abstract population. I think an easy way to think about it is it's just values you can't rule out at your chosen significance level. So if you've chosen p equals 0.05, then all of the values within the confidence interval are plausible with that significance level. So it's a range of probable values given your significance level. That's a bit of a woolly definition. That's because there's a lot of debate about exactly how you should define it, but I don't think it's that important for you guys to think about. So confidence intervals are great because they help us interpret certainty, clinical significance, and plausible ranges all in one. The wider your confidence interval, the lower the precision of your estimate, your central estimate. If you think it's 5, but your estimate is minus 1,000 to plus 1,005, obviously your precision is completely whack. Whereas if your confidence interval is very narrow, you can be a lot more precise and certain that it lies within a narrow range, and it's much easier to make decisions based on that. It additionally lets us see clinical significance. So does clinical significance lie within the bounds of our confidence intervals? And I'll talk a bit about why that's important just after this. And also plausible ranges. So yeah, like I said, how plausible are the range of values that your actual difference could take? So in reality, working out exactly what is and isn't clinical significance is itself a very active field of study, which we won't get into too much detail in here. But we're going to run through some examples of how to interpret confidence intervals. For the purposes of all these examples that we're going to do, we're going to accept that 5 millimeters mercury is a clinically significant reduction in blood pressure. And so what that means is, in essence, we're not really interested in changes in blood pressure that are less than 5 millimeters mercury, because although they might be statistically significantly different, it doesn't really affect a patient, we've decided. Whereas we are interested in differences more than that. And we're going to accept that, and that's going to help us work through the subsequent examples. So for our first example, we've got medications A and B. We're comparing them in a trial, and we found a significant result. Go us. And there's a mean difference of 15 millimeters mercury, and we've got a 95% confidence interval, and that's 1 to 29. And remembering that our clinically significant effect is 5 millimeters mercury, can we be confident that this medication has a clinically significant effect? I'll give you 5 seconds to decide in your head. The answer is sort of no, because although we can be relatively sure there's a difference, because we found a statistically significant result, this would only have happened 4.5% of the time if there was no difference, that confidence interval is quite wide, and actually the result we found is consistent with a whole ranges of differences, including really tiny ones like 1 or 2 that we're not that interested in. And the thing to remember is that p-value only tells us about the null hypothesis, so what is the chance there is no difference. It doesn't mention anything about clinical significance. It can't, because that changes. So although we can be pretty sure that there is a difference between this medicine B and A, we can't be sure that that's a clinically significant difference. And that suggests that maybe we need a little bit more research to clarify exactly where in that confidence interval does the difference lie. This is a second example. We've got medicines C and D, which we're comparing in a trial. And we find an insignificant result with a mean difference of 2 millimeters mercury and wide spanning confidence intervals all the way from minus 10 to 12. And this is obviously going to give us a very high p-value, which is listed here. Now, I'll give you a little time to think, can we be confident that these medications have similar effects clinically? What do you think? Well, again, no, we don't have evidence Because if you look at that confidence interval, the difference could be anything. The difference could be that C is better, the difference could be that D is better, we don't know. It's plausible that either of those things is true. Really what this confidence interval tells us is our study wasn't good enough and didn't have good enough power, and we weren't able to make our confidence interval precise. So this is really an absence of any evidence that's useful. It's not evidence that C and D are the same. And that's an important differential because, if you've got other reasons to suspect that C or D might be better, or if you're thinking about how do we need to do future research, this indicates yes, we need to do some more research because it's really not clear what the effect is here. For our final example, second last example, we're going to have E and F, which we're comparing, and they've got a difference of 15. The confidence interval is 6 to 24. We've got a good p-value. Can we be confident that E has clinically significant effects? What do you reckon? So the answer here is yes. That whole of that 95% confidence interval is all clinically significant. So we're pretty sure that the difference is above the threshold of clinical significance. We're pretty sure that one is better, and it's not just better statistically, it's clinically better as well. So we can be pretty happy that we've got the results we need, and probably not going to be a focus for future research, although obviously you want to evaluate it in the real world and to check that trial results hold up when being used in practice. So confidence intervals help us decide not just whether they're significant results or insignificant results, and that's based, I guess, on whether it crosses the 0 threshold when you're looking at difference. If it crosses 0, your p-value is going to be less than 0.05, more than 0.05. And if it doesn't cross 0, that's going to be the same as a p-value of less than 0.05. But why look at that for a confidence interval when you just have the p-values tell you that? They're much more than that. They tell us how important significant results are and how important insignificant results are. And that's much more interesting. So just to briefly rehash the examples, here you've got two significant results which are identical in terms of their difference and are both significantly statistically significant with p-values less than 0.05, and although we can see the bottom one there's more evidence for than the top one. But actually looking at the confidence interval tells us that E compared to F, we're really confident that E is better than F because that confidence interval, all of it, covers that clinically significant range. Whereas the first one, we're pretty sure there is a difference, but we're not yet quite sure how meaningful that difference is, and probably need to do a little bit of more work on it. In contrast, I've added another example here we haven't gone through, but these are both insignificant results, suggesting there's not enough evidence to say there is any difference. But our interpretation of them was very different. So with C and D, there's that wide confidence interval, so plausibly either one could be better. We just have an absence of information, we need to do more research. In contrast with G and H, we've got an insignificant p-value, and our confidence interval that we can reject ranges outside relatively well. The confidence interval is 4 to -2, and if we remember that 5 is the difference we're interested in, none of those values are 5 in either direction. So we can be pretty sure, as far as things go, that G and H are relatively equivalent according to our measurements. And so actually we have evidence of absence here. And that is, I guess, one of the critical things in thinking about those insignificant values, is that the top one's absence of evidence. We don't have any evidence that one is better than the other, but that's because we just don't have any good evidence. Whereas the bottom one is evidence of absence. We're pretty sure that these two are the same as far as clinically significant effects go, and probably we want to focus elsewhere if we're trying to find differences. So hopefully we've talked here a little bit about clinical versus statistical significance, what the differences of those are, and we've started to understand sort of maybe modern interpretations of the p-value as a gradated idea of becoming more or less significant rather than a binary interpretation. And hopefully you understand confidence intervals a little bit better and how we might use them to make decisions. So earlier in the section we also went over p-values, power, confidence intervals. We talked a bit about how to interpret them and how overall on a population scale that might end up being actually drugs we see, how effective are those drugs. And I have covered quite a lot of concepts here, so go back and have a look at them and make sure you're familiar with the definitions that we use. As always, thanks to Manny for helping with the design. These are where a couple of the resources I got were from. XKCD is a fantastic site, check it out if you haven't. Their comics are great. And again, lastly, this is a new lecture series. I hope it's helpful, but if it is or if it isn't, please give me some feedback, either by scanning the QR code or going on tinyurl, about what you liked, what you didn't like, if you'd like to see things on anything else, because that'll be really helpful. Thanks, guys.